All right, welcome everybody to this Let's Talk Meshing webinar. In today's webinar, we're going to be talking a little bit about the Stanford Solar Car Project's race for aerodynamic efficiency. So joining us today is Rachel Abril from the Stanford Solar Car Project. Rachel is the aerodynamics lead on the team and a master's student in mechanical engineering at Stanford University. She joined the mechanical team back in 2013, and for the most recent 2015 cycle, she specialized in grid generation for the aerodynamics team, performed mechanical design for the car, and was also a driver. For the next cycle, Rachel is leading the aerodynamics toolchain and hopes to get even more involved in the mechanical design of the vehicle. Thanks for joining us, Rachel. From the SU2 development team, we welcome David Manossavas. David is a PhD candidate in the Department of Aeronautics and Astronautics at Stanford University. He works in the Aerospace Computing Lab under the direction of Professor Jameson, and his research interests are in active flow control, aerodynamics of ground vehicles, aerodynamics and design of aircraft and UAVs, as well as numerical methods and shape optimization. Thanks for joining us, David. Also joining us from the SU2 development team is Dr. Thomas Economon. Tom is a postdoctoral scholar at Stanford University, where he received his master's and PhD degrees in the Department of Aeronautics and Astronautics. His research interests include CFD, shape design using adjoint-based methods, and high-performance computing. And Tom's going to be joining us during the Q&A session today. So thanks for joining us, Tom. From TechPlot, we welcome Scott Fowler. Scott is the product manager for TechPlot 360EX and TechPlot Chorus. It's his job to understand where the CFD and aerospace markets are going, gather customer feedback, and make sure that TechPlot develops products to meet those needs. Scott naturally stepped into the product management role after his tenure as the lead product architect for both of the tools that he now manages. Thanks for joining us, Scott. And lastly, my name is Travis Kerrigan. I'm a senior engineer with Pointwise, and my role is to work with prospective customers and demonstrate how Pointwise can be used to improve their CFD process. I also produce technical content such as this while working with customers and software partners to demonstrate best practices in grid generation, solver setup, and solution post-processing. So with that, I'm going to pass things over to Rachel, and she's going to begin by talking a little bit about the Stanford Solar Car Project. So Rachel?
Thanks, Travis. Stanford Solar Car Project was founded in 1989, and it's a completely student-run, nonprofit organization within Stanford University. What we do is we design and build a new solar car every 2 years, and we race in the World Solar Challenge in Australia. So we have team members across multiple disciplines, including aerodynamics, solar array, battery, mechanical, composites, electrical, and code, and so on. We have about 50 members who contribute, 20 core team members, and 16 or 17 who become a part of the race crew in Australia. So the Bridgestone World Solar Challenge is a 5-day solar car race, and it runs across the entire length of the Australian outback from Darwin to Adelaide. But it's not just 5 days. It's the culmination of nearly 2 years of engineering in multiple disciplines, including there's 2 months of race crew testing at home plus 1 month of testing in the outback. And this is to ensure that the car's systems have been integrated and that the race crew is trained to be a well-oiled machine. Arctan was Stanford's 2015 solar car that competed in the most recent 2015 Solar Challenge. And this is Arctan at the Aerodynamic wind tunnel. So there are 3 big factors key to winning the race. After reliability, which if your car breaks down, it doesn't matter how fast you are. Aerodynamics and solar array basically define the speed of the vehicle. And aerodynamics and array can sometimes have competing interests when designing the car, and we do systems analysis to try to find a good compromise. Stanford competes in the Challenger class, which means that the first to finish wins. The car fits 1 driver and that's it. It's extremely minimalist. If something doesn't make the car go faster, it doesn't go on the car. Now, Arctan was the first time that the team brought the entire aerodynamics toolchain internal and learned to do everything ourselves thanks to our partnership with the SU2 guys. And here's the Aero sub-team hard at work. Aerodynamics is the first thing to happen and the first due date in a solar car cycle. So those of us on the Aero team really got to follow the car's design from start to finish. Beginning in the summer of 2014, we had meetings every Wednesday night in this very conference room. And it was a small group of about 8 of us, and we did over 40 iterations, finally shipping the aero body the following December. So here's an overview of the tool chain that we used for each iteration. Like I said, this past cycle, our aero tool chain got started internally for the first time. Our team had already always done CAD servicing internally, though this part of the tool chain is reliably the most time-consuming part. And then we used Pointwise for meshing, SU2 for CFD, and TechBlot for visualization. Some challenges that we always face and did face this past cycle are the packaging of necessary mechanical components like the suspension and driver, along with race regulations that will tend to limit aerodynamics. So we always have to figure out ways to work around these things. The basic numbers that we're always aiming for are low drag and zero lift. So once the car was built and rolling, we took the car to Aerodynamic wind tunnel and verified our CFD numbers. And as you can see from the video, here's us doing some smoke wand tests to visualize streamlines. And here's a clip of us using tassels to visualize separation. Finally, we took the car from simulation to reality. We put about 4,000 test miles on the car to shake it out for bugs and also to train race crew for their convoy jobs and to get the solar car drivers really familiar with the car. Now here's us at the Thunder Hill racetrack. And then here we're finally on public roads in the Central Valley going at cruising speeds. And now you can see one of our drivers getting prepped to drive, getting the radio configured, and this is actually me driving now. And now Travis is going to talk about how Pointwise's mesher was used for our team's CFD pipeline.
All right, thank you very much, Rachel. So I want to preface the discussion on meshing by saying that Rachel's actually the one who generated all of the meshes. So she mentioned that they did over 40 different designs, meaning she did over 40 different meshes, each one taking about an hour and a half to do. So what I'm going to be presenting are some of the techniques that she used, but also in preparing for this webinar, her and I started discussing some techniques that they plan on using moving forward, so I'll be presenting those as well. So this is the first thing Rachel would see when she imports that SolidWorks file into Pointwise, basically a model of the car consisting of a number of different surfaces. The next step is what's called solid modeling, and their geometry is very clean. So it came in easily assembled into a single watertight model representing the vehicle and consisting of 46 quilts. Now, those of you unfamiliar with Pointwise, a quilt is basically a logical meshing region. It's a piece of topology relating underlying trim surfaces to one another so that when that model is meshed, each quilt gets its own domain. And a domain is a surface mesh in Pointwise bounded by grid curves where very specific distributions of points and things like that can be applied. And also boundary conditions can be applied for the solver or post-processor. So as you can see, meshing this one model consisting of 46 quilts results in 46 domains. And they don't necessarily represent like engineering surfaces on the car or areas where we would actually apply boundary conditions. So what Rachel ends up doing is joining quilts, assembling them into larger quilts that represent physical components on the car, like the left and right side of the canopy, the front of the vehicle, the top of the vehicle, the fairings, etc. And in doing so, she's really reducing the complexity of the resulting surface mesh, but doing all of this on the solid modeling side before a mesh is even generated. So once she's done this, meshing that model with 15 quilts would result in 15 domains, as you can see in that lower image. So here's a short little clip showing what that process looks like in Pointwise. So just confirming now that there is a single watertight model representing this car, and you can see there's one model, consists of 46 quilts, and 0 lamina boundaries, meaning no free edges or gaps or cracks or anything like that in the surface. Those would be highlighted in red in the display. In this case, it's a nice watertight representation of the car. And now the next step is quilting, basically assembling quilts into larger quilts that represent, physical components of the car. So like the top surface, left and right side of the canopy, And like I mentioned before, a quilt is a meshing construct. It's basically there for the purpose of meshing and sits on top of the underlying geometry, meaning that you can actually break these quilts back up into their original components because we don't destroy topology. And by joining these into larger quilts, you're not reducing any geometric fidelity. You're still meshing on the same geometry. So you really get the granularity that you need for the simulations that you're looking to perform. And so you can see now there are 15 quilts for the car. The next step is surface meshing, and Rachel elected to generate an unstructured triangular surface mesh for the car. In this image, we're looking at a top-down view of the vehicle and 3 different techniques for generating that surface mesh. The first being automatic isotropic curvature-based refinement, meaning you specify a turning angle between adjacent triangles, a deviation from the underlying geometry, and just let it go. And you'll notice that it starts to pick up, the leading edge curvature of the car, kind of coarsens things up on the interior, picks up the back of the canopy on either side of the trailing edge, but results in a ridiculous number of cells, in this case 264,000 cells to resolve this geometry. So what Rachel ended up doing is isotropic manual refinement. So she created a uniform surface mesh on the car and then just selectively refined the areas that she wanted to. So for example, the leading edge of the car, further coarsening things up on the interior of the mesh, picking up that canopy a little bit, and then the back of the car. And she was able to drive down that cell count by more than 50%, in this case down to 108,000 cells. So this is a very efficient way of generating a surface mesh. However, her and I got to talking, and there's an additional technique that could be used to drive down that cell count even more, and that's anisotropic refinement. So this bottom image, as you look at it, looks a little bit finer than the top two, but it has fewer cells still, in this case 77,000 cells, and that's because it was done using anisotropic refinement, meaning we're stretching cells and we're marching right-angle triangles away from boundaries. To give you an idea of what that looks like, in this image on the left, we're looking at the front of the car. On the left is isotropic refinement. If we wanted to pick up the leading edge of the vehicle, points would have to be stacked in the spanwise or tangential direction to resolve that curvature. And that's a really inefficient way of capturing geometry. Instead, using anisotropic refinement, you can see that we're not stacking points in the spanwise or tangential direction. We're actually stacking them normal to that boundary and growing these right-angled triangles away from that boundary, and that results in fewer cells. Here's a shot of the back of the vehicle showing this technique was used on the back of the canopy, on either side of the fairings, and the back of the car itself. Again, really driving down that cell count. And if you think about it, when we generate a volume mesh, we're going to be advancing off of this surface. So if we can reduce the surface cell count, we can reduce the volumetric cell count as well. Here's a clip showing this in action. Now, this is a technique that we call 2D T-Rex, and T-Rex stands for anisotropic tetrahedral extrusion. It's actually our 3D viscous meshing technology, but there's a 2D equivalent that we call 2D T-Rex. And so what we're showing here is generating just a uniform, unstructured surface mesh on the vehicle. Going to go ahead and organize it, put it in its own layer, and then go to Grid T-Rex, and we're basically going to grow these cells away from the leading edge of the car. So we've selected those domains, and we can go to Grid T-Rex, and what we're going to specify here are the number of layers, the growth rate, and then we're going to pick the boundary that we want to grow these elements away from and specify an initial spacing. So it's that initial spacing, the growth rate, and the number of layers that are going to determine the profile of those right-angled triangles away from that boundary. So I'm going to skip ahead here so you can see what that looks like. So here you can see these right-angled triangles being grown away from that leading edge, and rotating it around, you can see that we do a really good job of resolving that curvature in a much more regular and less faceted fashion. So Rachel had mentioned that they studied over 40 different designs for the car, and some of them were significant deviations over the previous iteration, some of them were smaller deviations. And for those that were smaller deviations that were maybe parametric changes of the underlying geometry, they can use what's known as database associativity to rapidly recreate that mesh. And basically what that is, Pointwise is a bottom-up mesher, meaning we start at the geometry and build a surface mesh and then build a volume mesh. And it gives us a lot of control over that process. And at the base level, there sits the database, which is the geometry. Once that's meshed, you get a surface mesh on top of that geometry, and in this case, we meshed a model, and a watertight model at that. So that means our surface mesh is also watertight, and examining it, we can see that it's 100% database constrained to the underlying geometry. And we can take advantage of this. We could actually export this grid as a Pointwise project file, and the database associativity is stored in that file, meaning each grid point and its associativity to the underlying geometry is retained in that file. So if the team elected to, say, parametrically change the height of the canopy of the car and the rest of the topology remained untouched, read that back into Pointwise, and appended that project with the mesh that they had exported, that mesh would snap back to that underlying geometry. Not only that, Pointwise is smart enough to know that the canopy dimensions changed, and it didn't just stretch triangles on the surface, it actually refined that mesh. So you get the same level of refinement as you got with the original mesh. Okay, so that allows you to reuse a mesh that's already been created for a parametric change in the geometry. Now, what if the team elected to completely change the topology of the canopy, introduce new surfaces, an entirely new geometry? Well, again, because Pointwise is bottom up, you start with grid curves, you build out your surface mesh, you build up your volume mesh. We can just go ahead and delete the surface mesh or the domains that sit on top of that canopy. Okay, so all that's left are the domains for the car, load in that new canopy, and then mesh the canopy and stitch the two grids together. This is extremely important for design optimization, where you want the bulk of the mesh to remain untouched. Because when you're running a calculation, you want to know that the changes in the solution are coming from the changes in the geometry, not necessarily changes in the mesh. So keeping the majority of the mesh the same is really important for design optimization. So here's a video showing that process. So we've gone ahead and deleted the domains off of the canopy, loaded in the new canopy. Going to go ahead and remesh it. So just put a uniform surface mesh on it. We could add some refinement if we wanted as well. And then the next step is to use the grid merge tool to basically stitch these two meshes together by using a tolerance, basically a distance between these adjacent grid points. And that will kind of create a nice manifold surface mesh. So I'll skip past that and show you that we can select all of the domains and examine the database associativity, and you'll see that it is 100% constrained to the underlying geometry. All right, once that surface mesh has been created, the next step is volume meshing, and in this case, Rachel elected to use T-Rex to generate a hybrid viscous volume mesh for the car. Now I'm going to walk through 6 recommended practices for using T-Rex, starting with the surface mesh. So the first thing you want to look at is the surface mesh quality. Why? Well, you're actually going to be growing elements off of the surface mesh. So if you can guarantee that you have a very high quality surface, you'll kind of guarantee that you get a very high quality volume mesh. It's going to go a long way to helping you generate a very high quality volume mesh. So the first metric we like to look at is the area ratio, and it's recommended to keep the area ratio less than 4 everywhere on the surface when using T-Rex. So the area ratio looks at the ratio of cell areas that are adjacent to one another, so 2 triangles side by side, sharing an edge. And by keeping this less than 4, you're basically ensuring that you have a nice, smooth surface, no massive discontinuities in cell area or anything like that over the entire surface. The next metric to look at is the maximum included angle, and we recommend keeping this less than 150 degrees everywhere on the surface. And this gives you an idea of kind of the skewness of the cells on the surface, and it's a little bit easier to visualize. Okay, so these 2 metrics, the area ratio and the max angle, are 2 metrics to look at on the surface before you even think about generating a volume mesh. The next step is to assemble your watertight computational domain, and we call that a block. So Rachel went ahead and built out the far field mesh. You'll notice that she put a refined domain underneath the vehicle to constrain the cell sizes in the vicinity of the car. And then using automatic block assembly can create this watertight representation of the computational domain. And it's empty by default because unstructured grids are going to be stored explicitly, and we don't want to populate that domain until you tell us to. In this case, Rachel wanted to populate that block using T-Rex, our hybrid viscous mesher. So in this case, she'll specify the number of layers that she wants, the growth rate, some quality criteria, the initial spacing off of the body of the car to achieve the y+1 required by SU2, and then initialize. And in this case, it generates about 6.5 million elements in 3 minutes on a laptop. So it's a really quick operation to generate a hybrid viscous volume mesh for this vehicle. Once that volume mesh has been created, the next step is to look at its quality. So rather than exporting it, looking at it in another tool, and then bringing it back into Pointwise to maybe fix any issues, you can look at it directly within Pointwise, and one of the metrics we like to look at is the maximum included angle. In this case, the max value is 167 degrees. Looking at the histogram, we see that this is a very high quality volume mesh. The next metric to look at is the centroid skewness. In this case, the max value is 0.84. Again, looking at the histogram, we can confirm that this is a very high quality volume mesh generated for the vehicle. Something I did want to mention for those of you joining us today, kind of a sneak peek at Pointwise version 18 is quad and hex dominant meshing. So in Pointwise version 18, you're going to be able to generate these quad dominant surface meshes. It's going to allow you to drive down cell count even more, but also maintain orthogonality and flow alignment, and then generate unstructured hexes in the boundary layer that transition to isotets in the far field. Again, kind of a sneak peek at version 18 for those of you joining us today. The last step is setting up the boundary conditions and then exporting to the solver. In this case, Rachel set up the solver as SU2, meaning that when exported, we're going to export the native ASCII.SU2 file. And then she could also have specified CGNS because SU2 can read CGNS files. And because she set up her quilts and domains early on in the process, not only can she specify boundary conditions for the inlet, outlet, far field, etc., but also instead of just one boundary condition for the body of the car, she can have separate boundary conditions for each of the domains for post-processing purposes. As you can see here, the bubble or the canopy has been put in a boundary condition, the fairings, etc. And then on export, there's an option to combine anisotropic tetrahedra. Now, T-Rex actually generates right-angled tets in the boundary layer and then transitions to isotets in the far field. And by turning on this option on export, you're actually going to be combining those right-angled tets in the boundary layer into triangular prisms on export, basically improving your cell quality in the boundary layer region. Okay, so with that, I'm going to pass things over to David, and he's going to talk a little bit about how SU2 was used for this application. So David?
Thanks, Travis. So first up, let's talk a little bit about what is SU2. SU2 is an open source collection of C++ software used for multi-physics simulations as well as for designing unstructured meshes. And kind of one of the main reasons we use SU2 is for computational fluid dynamics and CFD. SU2 is under development here at Stanford in the Aeronautics and Astronautics department, but it's also being used and developed all around the world. Click. Since we released it in January 2012, we've had over 350,000 web visitors over 172 countries. We literally have tens of thousands of downloads, around 7,800 email addresses on our user list, and we have people in the developers list and currently developing the code in over 140 of them all around the world. And the main reason we have been able to push this code and continue with this project is because we've decided to keep it open source. And on top of that, we'd like it to be really easy to install and really portable, so we've kept that in mind when developing. By the use of C++, we'll be trying to make it very readable, really to reuse it, as well as to encapsulate it into libraries that can be easily modified and moved around. Using Python, we'll be creating wrappers around the code. We've started to introduce more flexibility to the code as well as automation, especially when it comes to design. And since a lot of the people who use SU2 would like to be able to scale it to bigger clusters, we focused a lot on high performance to make sure that this code is capable of running really large cases and give you valuable results. We really believe in the open source culture because it really has tremendous potential. It allows us to be able to tap into the talent of people all around the world without needing to have an actual geographical connection. And by keeping it open and in web-based platforms like GitHub, we really remove geographical limitations when it comes to collaborating. And this, at the end, increases the pace of innovation in computational sciences as well as in CFD. Thanks to all that collaboration and all the work we've done on people all around the world, our code right now is able to handle a lot of different regimes of flow. Some of the examples that we're giving here and that we've published on is on transonic flow, such as the Airbuses and Boeings of the world, big commercial airplanes that are going really close to the speed of sound. We've done some work with supersonic and N+2, N+3 type concepts on which we are trying to design to reduce drag as well as to reduce the acoustic signature on the ground. And one of the examples that we're actually talking about right now is incompressible, where we are designing and working with vehicles, ground vehicles. And once we decide on our application, in this case the solar car, it's simulation time. The idea is to be able to take SU2, put it in a computer, and start working with that. And the way how you'll go about it is going to one of our websites where we host the code and be able to get a distribution, starting from the binary distribution, on which it will give you the chance to be able to taste a little bit of what is to work with SU2. It has limited features, but it's a good way to start. After you get your feet wet with this, you can go to the source code, be able to download it directly from GitHub, and be able to start using parallel computing as well as to control more of what the code's doing for you. To get you started, we have a wiki as well as tutorials that will be self-explanatory and will help you really start using all the features available to you in SU2. And if there's any questions, we also have a CFD online forum in which you can share with the community as well as with us and other developers around the world. So once we put SU2 in a computer, you take a mesh like the one that Travis has shown you how to do. You need to develop a config file, which is really a text file. And in this webinar, we've decided to just kind of walk you through some of the most important features of this config file for the case of incompressible flow over a solar car. So one of the first things to look at when you open the config file is the type of physical problem. Since we're trying to model real air over the car, we want to use the Navier-Stokes equations. And due to the regime at which the car is moving, we want to choose a turbulence model, in this case choosing this polarity alma maris. And like I mentioned, the regime on which this vehicle is being simulated is incompressible. In addition to that, on an incompressible solver, to be able to determine the conditions at which the car is going to be moving, we need to specify the free stream density, the free stream velocity, and the free stream viscosity. In that way, our solver knows how to simulate the flow around the car. Once that has been specified, it's the turn to specify how are we going to treat the car. In this case, we're using this markers to determine how we're going to specify each portion of the car. We are combining the body, the bubble, the fairings, and we are specifying them as heat flux of 0. In this case, we're guaranteeing that it's a no-slip boundary condition. We are allowing boundary layers to form, mimicking what will happen in real life. We choose the inlet to be the free stream velocity, as we are trying to model here a wind tunnel, and then the outlet to make sure that the flow can go through one end of the wind tunnel and exit the other one. And to model the wind tunnel, the ground on the walls, we are assuming a slip boundary, as most wind tunnels nowadays have boundary suction conditions on which they eliminate completely the boundary layer. And this is what we are achieving by creating a slip boundary on the ground and the walls. In addition to that, when we are doing some of the post-processing and when we are looking at our simulation and its convergence, we are interested in looking at the forces in the car itself. And that's where marker plotting and marker monitoring come to play, as we are selecting all the surfaces of the car to be able to track how is the convergence of the integrated forces in those particular surfaces, as well as writing them on a history file that will be opened up later. After that, we need to choose a numerical method. In this case, we've chosen the row scheme and second order, and we've, as well as using a first order turbulence model, which are just the industry standards when using CFD. And then finally, we have to specify what's going to be our inputs and what are going to be our outputs. In the case of the solar car, we're using an SU2 or a data SU2 format mesh named Soundwave 40, and we're specifying that the format that we're using is SU2. And like Travis mentioned before, we can also support CGNS files just by changing the name and the format within this config file. And for the output, we've chosen to go with TechPlot binary. And the main reason for going binary over ASCII, which we also support, is because it's faster to right? It's faster to read, as well as it uses less space in your hard drive. So once we've set up the config file and we have our mesh, we can go to our command line and just start running the case by using one of our Python scripts if we want to do it a little more automated with different processors. In this case, we are using 100 processors. And once we click enter in this line, our code will start running. We'll be able to see iterations, the time it takes for iterations, the evolution of the residuals, as well as the evolution of our integrated forces. One kind of rule of thumb that we have is to not use more than 5,000, or sorry, less than 5,000 points per core. And this is just to try to maximize the output or the computational resources that we have. But once we've actually gone through the process and being able to install SU2, we've run SU2, and as a result of this computation, we're going to get a couple different files. But the ones that I want you guys to focus on are on the history.plt, which, as the name says, is a history of the conversions of the file on each iteration, flow.mesh, and flow.sol, which is a combination of binary files that will give you the solution on the volume, as well as surface flow.mesh and surface flow.sol, which is a combination of binary files that will give you the solution on top of the car. And to be able to visualize it and get a picture like the one that you're seeing on the screen, we'll use something like TechPlot to be able to see the trends and start making design decisions. And with that, I'd like to pass it to Scott from TechPlot to tell you a little more about it.
Thanks, David. So again, my name is Scott Fowler from TechPlot Incorporated. We've been in business for about 34 years now, founded by Mike Peary and Don Roberts, pictured there on the left. They're actually Stanford graduates, so it's awfully nice to be here talking about the Stanford Solar Car team and SU2. So to understand SU2 results, the Stanford Solar Car team used TechPlot 360EX. The first thing that they needed to do was understand if their CFD ran correctly. So they used the history PLT file that David just mentioned to look at their residuals. So here you have a nice line plot looking at the residuals. They were also looking at the integrated quantities. They wanted to minimize drag and get lift very close to zero. So here's a plot of the integrated quantities. And then finally, they're looking for areas of drag on the vehicle. And that's commonly visualized by looking at pressure contours, which you can see here, as well as streamlines. So how did the Solar Car team use TechPlot 360 in their design iterations? So they had a pretty nice process set up where they would do each design iteration, and they had a set of predefined images that they could create using TechPlot layouts. So a layout is just a set of instructions to tell TechPlot 360 what data to load and then how to represent it in the view. So you can see a couple of images here that they created. The one on the left is, again, surface quantities of the pressure coefficient and streamlines going around the vehicle. And then on the right, they have a number of different views of the vehicle, again, showing the pressure contours. So in working with the Solar Car team, they wanted to understand other ways to visualize their data to learn more about it. And we'll talk about that in just a second. So again, as David mentioned, prefer binary over ASCII. ASCII has its place. It's quite easy to read, human readable, but it's quite slow to load, especially for large data. So it's best to use binary if you have 2D or 3D data. ASCII is fine for line data. And as you can see in the table below there, the vast benefit of using binary data. So when we first engaged with the Solar Car team, they were actually exporting ASCII, and they're much happier with the binary form now. So you can see the binary PLT format, that's the middle column. You can see the files were about half the size. Load time went from about 5 minutes down to 2 seconds. So that makes everybody happier. And then the amount of RAM used was even less. Now, in the over the last couple of years, we've been working on a new binary format that we call Sizzle. The extension is SCPLT. That one has even more advantages over the binary PLT form. You can see the file sizes are even smaller. We achieve that through node map compression for unstructured data. The load times can be orders of magnitude faster for very large data. The Stanford solar car grid was only about 7 million points, so that didn't result in orders of magnitude faster load times, but we have seen orders of magnitude faster load times for data sets on the order of 100 million or even billion cell cases. And then one of the really critical things with this new binary format is we use much less RAM. So you can see the RAM overhead here is very, very small. Even for a 500 million cell case, you can load that with under 2 gigabytes of RAM. So you can now make the impossible possible using the SCPLT format. So how do you get your data into binary form? As David mentioned, you can configure SU2 to use TecPlot binary, as he pointed out in the config file. SU2 takes advantage of a library that we produce and freely distribute called TecIO, which can allow you to write out the PLT form as well as the sizzle form of the data. You can also convert your data to binary using preplot. Preplot is an executable that is distributed with TecPlot 360. It's not licensed, so you can run it free of charge. And it's a very simple command line tool. It takes as the first parameter an ASCII file, and as the second parameter the resulting file that you want to write out to. And then finally, you can always read your data into TecPlot 360 and write it back out. So moving on to actually some new visualizations that we've helped the solar car team create. This is one using stream ribbons. In their previous visualizations, they'd been using stream rods. Ribbons are interesting because they help you visualize turbulence. You can actually see twist in your flow using a ribbon. A ribbon is actually 2 streamlines seated right next to each other, what we call a core streamline and a sidecar. And then we stitch those together to create a surface. In this view, you can see that there's not a whole lot of twist in those ribbons, so a nice steady flow going over the vehicle. You can also use stream traces on the surface, and here we've used stream traces to create a simulated oil flow plot. Some people refer to an oil flow plot as line integral convolution, and we can simulate that using our stream traces. And what we've done here is we've seeded 5,000 stream traces on the surface, and then we've limited the length of those stream traces. We'll show you how to do that on the next slide, but here you can see at the bottom image on the right, you can see an area of recirculation, and this type of view can also help you find areas of separation. So moving on to how we achieved this effect. Here we're setting up the surface coloring using some of the right-click context menus that have been added to TecPlot 360 EX in recent years. We go into the stream trace dialog, making sure to set it up for surface lines, and you can see where we set the 5,000 seed points on the surface. And we'll go over to the integration tab and set it to a short length of 50. The video skipped on my end, so hopefully you saw that on yours. Set up the vector variables, and finally create the streamlines. Then you can see that there are the arrowheads on there, so we'll just turn those off, and we'll have a nice view of the streamlines and looking like the simulated oil flow plot. So this area of recirculation that you're seeing at the back end of the canopy, this is a feature that the solar car team had not seen before because they weren't aware of this technique. And this could be an indication of an area of the vehicle that they could change the geometry of and possibly reduce drag. So we'll move on to automation and analysis. So TecPlot 360 has a fairly robust macro language, so you can automate many of the plots that you've seen here today. You can use these macros to run at the tail end of your CFD simulation, so you can have a suite of images ready for you at the end of your CFD run, so you can get a jump start on your analysis. And what we're showing here are plots that are span-wise lift on the vehicle. So this is a capability that is not directly available in the TechPlot 360 user interface, but something that you can do with the TechPlot macro language, and shows the power of what you can do there. So this plot is particularly interesting to the solar car team because they are interested in side wind conditions. They need this vehicle to be stable when the wind is blowing sideways, as it can do in the Australian outback. So in order to generate these plots, what we do is we actually create 70 slices across the width of the vehicle, and then we run a macro which will extract those slices, integrate the pressure of those slices to calculate your lift, and then we put each one of those values on a line across the vehicle. And on the next slide, we'll show a quick animation of how to do that. So here we're using the slice dialog to create slices in the Y direction. We're using start and end slices to bound the width of the vehicle. And then we put 70 slices in between those. So we have a total of 72 stations across the width of the vehicle, or the span of the vehicle. On my end, the video has stalled, so I'll just keep talking through it. And then we go through and we run a macro, and the macro in the back end will do all the calculations that I mentioned on the previous slide and end up giving you this nice image. And again, this is something that you can tack on to the end of your CFD run and have these images waiting for you for each design iteration. So I'll pass it now over to Rachel for some conclusions.
So ArcTan ended up finishing 6th in the World Solar Challenge this past cycle. And based on race strategy data, it was our fastest car to date, but there's still a lot of room for improvement. And on the whole, our team is looking to take every aspect of the vehicle to the next level. Better meshing techniques on the aerodynamics side mean we're going to be more efficient computationally and more likely to converge. We want to take advantage of SU2's advanced features this time. We'll lay out a little bit of time for that at the end of our Aero toolchain, our Aero cycle. We want to look more into sensitivities rather than just large-scale changes for mechanical component changes. And like I said, aerodynamics is the first thing to happen. It affects everything else on a systems level, from solar array performance to mechanical packaging to vehicle handling. And we want to do that analysis from the very beginning in tandem with our aerodynamic iterations. If you're interested in following our progress, you can follow us on our website or on our Facebook page. Thanks for listening.
Thank you very much, Rachel. And thank you all for attending our webinar. I did want to mention that a recording of this webinar will be available on our website by April 8th. You can access that at pointwise.com/webinar. If you have any questions about the Stanford Solar Car project, you can contact them at their email address. If you have any questions about Pointwise, you can email me. Any questions about SU2, you can directly email David. And if you have any questions about TechPlot, you can email Scott Fowler directly as well. Something I did want to mention before opening it up for Q&A is our Pointwise user group meeting coming up in September. It's the 21st and 22nd of September. This is a fantastic 2-day event that includes a training component as well as technical presentations. So if you're a Pointwise user, definitely submit an abstract. The call for papers is now open. So I'm going to leave this slide up during the Q&A session. If you have any questions, please type them into the questions dialog box. I will read them and the appropriate person will answer them. And we'll do this for about 10 or 15 minutes before concluding the webinar. And if you have any additional questions, you can jot down these email addresses and email us as well. So it looks like a few questions have already come in, so I'm going to read some of these. The first one is, could you please explain how modern wind tunnels for land vehicles approximate the floor moving with the inlet velocity?
I can take that.
Okay.
So the way how modern wind tunnels do it, there's actually 2 different ways, but the most common one is there's a system of blowing and suction on the floor. And in this way, they eliminate the boundary layer. And the hope in there is that when you are driving into the road, you are not seeing a preformed boundary layer in there. So by removing this, you are narrowing the gap between what you're testing in the wind tunnel and what you're actually testing or what you will be seeing when you're driving a car. Now, the other way that's a lot less common, but it's still done in some places, is actually installing a moving floor that will move at the same speed as the car. Now, the way how we tested the solar car was on the former, with a system of blowing and suction that removes the boundary layer, closing the gap between what you will see when you're driving and the actual test setup.
Okay, thanks, David. Here's another question. Was there a design target to place the total drag force vector in the middle of the vehicle between the left and right wheels? Rachel, David, or Tom?
This is Tom here. I can take this real quickly. We did some side wind testing, which is maybe related to this topic. We wanted to make sure that the performance was robust when we had side winds for the vehicle. We didn't want to have any large moments, although the car was relatively heavy compared to, aircraft. We're usually concerned about getting weight down, but for this, we weren't as concerned about weight, and we knew that we could kind of live with some pretty high forces and without having too much concern about kind of things being offset. There was a slight asymmetry, of course, with the bubble being on one side, but it was pretty minimal compared to the other forces.
So we didn't necessarily work towards placing the lift vector in the center of the car, but we did look into the stability to make sure that it wasn't placed too far to the sides. It ended up landing in the middle anyway.
Okay. Here's a pretty good question. This guy is asking about whether or not, let's see, the role of radiation in the solar car simulation, CFD simulation, was it considered or not?
No, we didn't really consider any of the radiation or heating on the car. We actually treated it as a zero heat flux surface. What we did consider was that there will be a boundary layer forming on it. So it's more of the aerodynamic side without really looking much into the thermodynamic side of it.
Okay.
We didn't do any high fidelity radiation simulations.
Okay.
We
Okay.
had simpler models that the team was using to estimate the performance of the solar array.
Okay, because there's a follow-on question to this too, so maybe we should ask about the future. The same person asked, he's wondering about the trade-off between aerodynamics and acquiring more solar energy and whether that might be considered moving forward. For example, acquiring 2% less drag or acquiring 2% more solar energy.
Right, so we have a chart basically kind of laying out our race minutes to percentage of improvement on solar array and aerodynamics, along with other components of the car that to a lesser extent will make the car go faster if improved. And so yes, every cycle we do look at that, and we use programs that have been created by our alumni to look at solar array performance for a given solid model for the top surface of a given model that you've seen here today.
Okay. Let's see. Can you explain the whole automated Pointwise project to load in a new mesh and a new geometry? Yeah, so basically with that, what we were demoing was if you generated a surface mesh on a watertight model and confirm that it is constrained to that geometry. If the topology of that geometry doesn't change, what you can do is you can load in a new geometry. If you need to, you can quilt it back up so it's identical in terms of its surface topology and also the quilt names. And then you can just file open the grid that you saved off, and a little dialog box will pop up and you can click append, and that'll just append the mesh to that project file and it'll snap to the underlying geometry. Again, the topology and the names have to be identical. So if you do that and you see grid kind of jumping to some other location on the car, that means that your geometry isn't topologically identical to what it was before. So this is why it works really well with parametric changes. So in your CAD tool, if you've parameterized surfaces, so you can tweak a parameter and it'll just update the surface, not introduce any new curves or topology or anything like that, just update the surface and move the XYZ values of the UV coordinates around, then export that and import that into Pointwise, it would be identical and the mesh would snap to it. If you're introducing any new topology, like I showed in the next slide after that, you would need to remesh the geometry. Let's see. Okay. I saw that during meshing of the design, you didn't consider the tire. You just have a flat surface on the bottom. Could you elaborate on that and maybe why that approximation was made?
I can take that.
Okay.
So we chose to make that simplification last cycle because we were fairly new to the whole aero process, and so also that configuration is closer to what we had in the wind tunnel, which is not a rolling wheel wind tunnel. So so that simulation was closer to the wind tunnel test, but this cycle will also be looking into whether having rolling wheels will change our design decisions, because you know, if the wheels don't change how we decide which car is better or worse, then it may not affect our end better or worse aero performance.
Mm-hmm. Okay. Let's see. Did you all use the optimization features of SU2 to optimize the car and the design of the car?
So near the end of the process, we got, I would say, up to high 30s of design counts before we started to attempt to run some of the adjoint-based design that we have in SU2. So we did successfully use a little bit of the continuous adjoint in SU2 to sort of guide our design decision. So what we would do is compute the surface sensitivities on the vehicle surface, which tell you sort of whether to push in or pull out different places on the body in order to reduce your functional like drag. And so we use this kind of manually to make tweaks, and the team was able to pull that information back into CAD and deform things to get better performance. Right at the end, we were starting to use some of the deformation, some of the automatic shape design capabilities, but we didn't quite have enough time. So we really only got to exercise some of the stuff manually. But I know the team really wants to look forward to using that next time. They're really looking forward to it, so we're going to get there.
Okay, thanks, Tom. Let's see. Can you comment on the choice of Spolart-Almaras turbulence model for CFD rather than, for example, K-omega?
In reality, this choice was made due to our previous experience and experimentation on how these models behave. The way how we go about choosing it is running similar simulations with different turbulence models and comparing those to available experimental data for more canonical cases, like separated flows or airfoils. And in this case, we chose to go with Spolart-Almaras because it's the one that was behaving the best and was giving us the closer type of simulation or the closer type of result compared to experimental simulations, as well as it being a simple and very robust turbulence model that is used in industry constantly. We also had some help when choosing the tools for people from industry, especially from Volkswagen, and that was kind of the consensus on which turbulence model to use and which numerical models to use, really.
Mm-hmm. Okay. Let's see. You might want to also take this one too, David. How do you, maybe you can describe how you make a moving wall for the floor in the simulation setup.
So in the simulation that we did, we actually didn't create a moving wall. What we did was mimic what will happen if the boundary layer was absorbed. And the way how we went about doing this was by creating a slip wall in the bottom for the floor and for the walls. And what the slip wall is really an Euler wall if you're familiar with CFD. And what it does is it does not enforce a zero velocity within the wall. It only enforces no penetration. So the flow is not allowed to go past that wall, but it's also not being stuck by the zero velocity on the surface. So the effect that this creates is that the flow will just move parallel to the surface, parallel to the floor and the walls in this case, but will not be building a boundary layer. And as I said at the beginning, this approach was taken to mimic what a wind tunnel, a modern wind tunnel will do when it is suctioning the boundary layers and trying to eliminate those while still allowing the flow to move parallel to it.
And I'll add, if folks do want to run with moving walls, we do have a no-slip wall condition that you can use inside of the code that will let you set a velocity of the wall. So you can accomplish this both ways. We chose the flow tangency condition, but we do have examples of simulations where you can set a wall velocity with a no-slip condition. So that's in the code.
Okay. Rachel, maybe you can comment on this. Why is the canopy on one side and not in the middle?
So the simple answer is that we wanted the car's driver to be on the correct side of the road when driving on the wrong side of the road in Australia, if that makes sense. So we're driving on the right side of the car and the left side of the road, which is the proper configuration in Australia. We also did look at which direction prevailing winds would be occurring, basically across the entirety of the race, to see if we should consider moments. But the biggest factor was probably just having the driver be configured correctly for our race setting.
Okay.
One more thing that, sorry Travis, that we just wanted to chime in as well, is that by putting the car or putting the canopy on the side rather than the center, we could take advantage of the space already being used by the fairing, and in this way be able to reduce a little bit the thickness of the car, which in turn reduces a little bit the drag as well. So on top of it being a decision to be able to make it easier to drive, as well as to handle the winds, it was also an aerodynamic decision when it came to placing that canopy in one side or the other, as well as for the solar panel point of view, as it gives you the chance to not have the shadow on top of the panels at all times, which you'll have with a center car. So at the end of the day, it was kind of a compilation of factors that drove to putting the canopy in one side rather than in the center of the car.
Okay. Let's see. Some of these are duplicates. Let me go down a little more. Okay, is there a sample case provided with SU2, or are there plans to provide maybe like a sample automotive case with your code as one of the tutorials?
Right now, we don't have a full configuration for a car, although we do have several projects and people that are working on these things. So we have some simple incompressible cases that are in the test cases as we speak. I guess I would have to ask the solar car team if they have any dummy models that they'd like to share, but we do have other folks, including David, who's working on some incompressible automotive type calculations. So, if you contact us, we'd be happy to share things that we can. Those are a little bit large. They might be tough to post online, but we'll look into it.
Okay.
We also have some more canonical cases that represent kind of the flow regime close to what you will see in an automotive car. So it's not necessarily the mesh that will represent the car, but you can have the Ahmed body, for example, which is a simpler body with the same regime as what you will have with a car, and that is in the test cases.
Okay. Let's see. Here's another question. My question is, what would be the difference of using incompressible versus a compressible solver with equivalent Mach number? Would you get the same results?
Yeah, so we actually tried out both cases. So as folks probably know, SU2 is more traditionally a compressible solver. The numerical methods inside the code are sort of more traditionally for compressible flows. So we tried both the incompressible model that's inside of the code, which it's an artificial compressibility method, where it's still a density-based solver, but we sort of replace the continuity equation with a sort of a pressure derivative term. And we tried out both of these, and results, the Mach number was I think down around 0.1. It was borderline where we typically run compressible cases, and we just found that the convergence and the behavior was just more robust with the incompressible solver, so we went with that. That being said, you know, the Mach number wasn't so low that this was something you couldn't calculate with the compressible solver. We just saw the performance was being much better with the incompressible solver, so we went with it.
Okay, for this type of configuration, which mesh topology works best, unstructured or multi-block hex? So from my experience in the stuff that they're working on, studying over 40 different designs and meshing each one, at least for the first study that they did, kind of the hybrid viscous mesh approach that they took was the best in my opinion, because it allowed them to rapidly recreate a mesh using the same spacing constraints and things like that. If they started doing some more parametric studies, it might be more advantageous to generate a multi-block structured mesh and then swap in and out geometries and kind of reproject surface meshes onto updated geometries and things like that, or automate that multi-block process using a script. But again, in my opinion, if you're changing the configuration as much as they were early on, it's more advantageous to use a hybrid viscous volume meshing technique like T-Rex and the unstructured surface meshing technique, as it's more automated. Let's see. Okay, this is a really good question. How did the car feel the first time it was driven?
Geez, that's actually hard to remember the first time I drove the car. But other than having very little airflow in the driver compartment, which is something that we don't want air flowing willy-nilly throughout the car. So we want our driver to get fairly toasty in there, which is probably the first thing that people notice is that you bake. And the second thing you notice is that while regular cars, they have quite a bit of rolling resistance to their tires, solar car tires have very, very little, so that they don't, so that they're as efficient as possible for straight line driving. And so the thing you notice the most is that, oh hey, I've let off the accelerator, but I'm not slowing down, which is a little jarring at first, but you know, it's great when you think about the goal of not losing any of that energy.
And Rachel, how close did it align with your expectation based on your performance analysis of the car?
Well, you know, do you mean from a, oh, this drag number equates to this sort of feeling of the car?
Maybe. or how fast it would go, that kind of thing.
Right, so that's a combination of solar array and drag, and so that kind of thing. So that actual just objective performance, things ended up aligning pretty well at the wind tunnel. You know, we verified that we've had 2 cars verified now, wind tunnel against CFD, and had pretty similar results. So, you know, we could kind of get the delta from that, and we did end up, like I said, having an overall improvement in the vehicle's performance. Now, it's really difficult to say in real life what percentage came from the array and what percentage came from aerodynamics improvement. And so that's always the struggle, that system's configuration.
Okay. Let's see. David and Tom, how long did it take to run one simulation?
Well, we were running in a big cluster that was one of our sponsors for Solar Car was able for. And I believe it took a couple hours when we were running the car using as many processors as we could. I believe for this car we're using around 200 processors, and in 1 to 2 hours we will be able to have a converged solution for the car.
Okay. With regard to sensitivities, which regions of the car had the greatest impact on the lift and the drag predicted?
Yeah, when we computed the sensitivities for the car, we were often looking at the leading edge of the fairings, the trailing edges of the fairings. Basically, you know, the sensitivities wanted to shrink the car. They basically said make it as thin as possible, get rid of all the volume, essentially. But we knew that some of the hot spots were the intersections of the fairings with the main body, right behind the canopy was something we were concerned about in terms of separation. So yeah, we mostly looked at how we could sort of do fine-tuning near those intersections of the fairing with the main body with the sensitivities.
Okay. In the wind tunnel, was it possible to see where the flow transitioned from laminar to turbulent, and if so, where did it take place?
Not necessarily the transition between the two of them. We did not have the proper equipment to be able to see that, like a small microphone to try to hear two acoustic signatures per transition. What we were looking for in the wind tunnel mainly, in addition to the integrated forces to be able to validate it with our CFD models, was separation. And that's why in the videos that Rachel showed, you can see us using a smoke wand and kind of passing it around the car to see if there were any areas that will become turbulent and separate, as well as putting the tussles in the car. We're more driven towards trying to find separation, which in this particular application is important since we're trying to streamline the flow as much as possible. Fortunately, after doing all that, we found out that, in fact, the CFD design actually worked fairly well to be able to eliminate separation anywhere in the car. But we were not able to really determine where transition happened. On the design mindset, we were hoping for a laminar flow for the first third of the car, give it or take, but it's really hard to actually say if we were able to achieve that or not.
Okay. Plans for a transition model in SU2?
Yeah, so we have one that's mostly complete. We have a couple developers that have looked at it in the past. We're still kind of picking at it. It would be, I would consider it in development mode still. But there is a branch on GitHub. If there are any developers out there that are familiar with some of the transition models, the Gamma RE Theta model in particular is the one we have mostly implemented. If anybody wants to help out finishing it off, let us know. But it's there. We're working on it.
Okay. Could you maybe elaborate a little bit on where people can download SU2 and what platforms it's available, just in case they weren't here for that part of the presentation?
Sure. So SU2, the code itself mainly lives in GitHub. So by going to the github.com/SU2 code /SU2, you will be able to go ahead and download the source code. I'll be able to see the wiki, the tutorials, as well as the instructions on how to install it, how to set up everything to be able to use MPI and use as many cores as possible. But if you're looking into binaries, we have those in our webpage. That's su2.stanford.edu under the download tab. And the platforms for which we have it available are Linux-based, like Macs, any kind of Linux distribution. And previous versions of SU2, we've had them available for Windows. And I believe this version that has just been released about a couple, like yesterday.
Yeah.
We just released a new version, by the way. And that one will be available for Windows hopefully soon as well. We are working really hard on trying to get that working fine. But right now we have them available for any kind of Linux distribution as well as Mac.
Yeah, I'm glad you asked. And yesterday we released version 4.1.1, and those are up now. The binaries are up. So check that out.
Okay, this is a really good question. Would it be possible to eliminate the wind tunnel and solely use CFD for this problem?
So far, we have been able to rely on CFD a lot. We have come really close to what the wind tunnel results have shown us. But my personal belief is that since we are using computational models and different geometries, and to a certain extent, we, with the computational side, will not be able to simulate separation, which is one of the big problems in CFD. in different areas, I think it's still important to be able to validate our results using a wind tunnel. Having said that, I think that the use of CFD reduces a lot the need for a wind tunnel, so you're able to perform most of the design using CFD and be able to have a fast turnaround. But I still believe that you need a wind tunnel at the end to be able to make sure that all your results make sense and that you are compliant with the physics.
Yeah, and what was great in this particular case about using the wind tunnel at the end was that once you built the car, you could actually dial in the ride height, you could dial in the angle of attack, all sorts of things that are real life effects for a real car that help the team get ready for the race.
And to add on to that, the discussion of whether or not going to the wind tunnel is necessary is a discussion about financial risk and risk to the car in transporting the wind tunnel from California to North Carolina. And whether or not that time and money could be spent putting it into making the car go faster in some other way, perhaps in solar array or even somehow in aerodynamics. So this is a kind of an overall system strategy sort of thing that we need to look at.
Okay. All right, last question. When using SU2, is there a method for plotting the residuals during the simulation, or can you only do that once the simulation is complete?
No, actually, you can always look it up and open it while the simulation is running. You can always open your history file and see how is it going, how's it doing. But you got to be careful when you do that to not overwrite it, because once you overwrite it, then you'll start having inconsistencies and the file will not continue to be updated.
Yeah, I mean, there are no GUIs, for instance, that are going to plot the residuals for you real time, but yeah, as David said, you can always open the history file. You can also sort of redirect your console output into a file and just have a little script that plots that for you. I play around with those kinds of things often just to check how calculations are coming along. But your typical scripting type stuff or looking at it in TechPlot is what we typically do.
Okay. Let's see. Okay, one last question. How is the design choice made to have one fairing on each side instead of having one fairing for each wheel?
So part of that is mechanical packaging and part of that is aerodynamics, right? So the decision to have a single long fairing on the driver's side it makes it significantly easier to fit a driver in the vehicle without cutting them in half. Then the decision to have two fairings or one long fairing like we did on the non-driver side, it was a decision about mechanical packaging and where does your battery pack go, how are you going to access your battery pack, and all the components that you're planning on putting on that side of the car. So for simplicity's sake, we ended up choosing the basically mirrored fairing approach. But as if you look up WSC 2015 cars, not all cars did that. Many did end up doing the symmetric fairings, but a couple teams did do split fairing, and that's something that we would actually like to look more into this cycle.
Okay. All right, I noticed that a few more questions came in about the canopy, and we kind of had a discussion about that earlier. So if you want to know a little bit more about that, I encourage you to email either the Stanford Solar Car Project or David or Tom at those email addresses that are up on the screen. So with that, we're going to conclude the Q&A session and the webinar. And like I mentioned before, the recording for this webinar will be up online at pointwise.com/webinar by April 8th, so you can watch that again. And we appreciate your time, and thank you very much for attending.